Hello, my name is McElrath. I solved spectral problem O using all the provided data from an IR spectroscopy, a carbon-13 NMR spectroscopy, and a hydrogen-1 NMR spectroscopy. Spectral problem O has the provided formula of C6H12O2. So let me walk you through how I solved it. First, I calculated the degree of unsaturation, also known simply as du. The formula is 2C, the C standing for carbon, plus 2 minus H, which stands for hydrogen, all divided by 2. So, remember, our formula is C6H12O2. So I use the subscripts plugged in to get the degree of unsaturation, which is 1. Now let's go ahead and take a look at those spectroscopies that I mentioned. First, looking at the IR spectroscopy, which just stands for infrared spectroscopy, the peaks in the IR spectroscopy help us identify different functional groups at certain points or peaks. There's a large peak seen at approximately 1750 centimeters to the -1, which to me indicated that there's a carbon-oxygen double bond, which suggests an ester carbonyl group. There's also 2 other strong peaks at approximately 1250 and 1050 centimeters to the -1, which also indicate an ester functional group. So now that we've seen the functional groups within the IR spectroscopy, let's go ahead and move on to the carbon-13 spectroscopy. As we see here, we have peaks, or also known as chemical shifts, that indicate carbons within a molecule. These peaks help me infer the functional groups as well as the molecules the carbons are attached to. I indicated that there were 6 in total, which goes perfectly with our formula. So, we have a chemical shift at approximately 171 parts per million, a chemical shift at approximately 70 parts per million, and then the rest are going to be at 34, 21, 20, and 19 parts per million. The first 2, which are at 171 and 70 parts per million, have a bonding environment that's indicative of a polar covalent bond. The rest I indicated as nonpolar covalent bonding environments. The first chemical shift goes along with that carbon-oxygen double bond that I mentioned earlier. The next, so the one at 70 parts per million, goes along with the carbon/methyl group that's attached to an oxygen. Next, that's a methylene group that's going to be next to that carbon that's double bonded to the first carbon. The carbon peak that we see at approximately 21 parts per million is an internal methylene group. The last 2 are at approximately 20 and 19 parts per million. Those are going to be a methyl group bonded to the carbonyl and a terminal methyl group separately. So since we have indicated more functional groups seen that go along with our formula, now let's confirm these with the hydrogen-1 spectroscopy spectrum. So, at approximately 3.75 parts per million, we are presented with a quartet that has an integration of 2H. The one indicated at 3H has an oxygen methylene group single bond, which is what we saw in the carbon-13 NMR spectroscopy. Our shift that happens at approximately 1.95 parts per million, that's indicated by the integration 1H, are going to be those two internal methylene groups. Lastly, the integration 6H indicated at approximately 0.99 parts per million and 2.1 are indicative of the terminal methyl groups and the acetyl groups. Those are going to be multiplets and a triplet, respectively. So our hydrogen 1 spectrum confirmed all of the previous interpretations from the carbon-13 spectrum. So let's wrap all these interpretations together. The infrared spectroscopy showed us ester functional groups. The carbon-13 NMR spectrum showed us additional functional groups, and the hydrogen 1 spectrum confirmed all of my interpreted functional groups, which led me to my proposed structure of N-butyl acetate. This molecule is known for its sweet and fruity smell, and it's actually used in nail polish remover. So that is how I came to this proposed structure of N-butyl acetate using IR spectroscopy, the carbon-13 spectrum, and the carbon-1 spectrum. Thank you.